What is going on, guys? Welcome back to the channel. In today's video, we're going to stick with our theme of solving some interesting interview questions. Our last video you guys seemed to really like, so we're going to stick with that theme today. So that said, start by dropping a like down below, hit subscribe, let's see how far we can get this year. We've got one day left, and let's jump into this question. So let's read the actual question first, and then we'll go through it together, think of the intuition behind it, and then we're going to solve it and take a look at the space-time complexity. So the question here is, given a m by n matrix, return all the elements of the matrix in spiral order. So first and foremost, m by n implies that our matrix won't necessarily be evenly wide by tall. So this one here is 3 by 3, but we could have something that's like 10 columns and like 2 rows. But if we just look at the actual figure here, I think this is pretty interesting because the arrows kind of depict what we're trying to do. So just reading it, 1, 2, 3, 4, 5, 6, 7, 8, 9, pretty simple, but we want to return a flattened array, a single dimension array of numbers, where we get 1, 2, 3, 6, 9, 8, 7, 4, 5. So it kind of does this like spiral looking thing as we traverse. And it actually gives you an example right down below. So our input is this two-dimensional array, which is our matrix, and our output is that. Now, looking at this, it's kind of interesting because the first thing that's glaringly obvious is we always want to move in this set pattern where we start at the top left, we go to the right, then we go down, then we go to the left, and then we go up, and then we do it again. We go right, and then we basically stop when we get to the center or when we get to some other condition. So with that in mind, let's go ahead and start writing out some code. So the first thing we're going to do is actually write the signature of this function. I'm going to call this spiral traverse. Hopefully I spelled that right. We're going to take in a matrix as an input, which will be a 2D array. And we're going to return a single integer array, and that is going to be our actual result. Now, the compiler will yell at us because we need to actually create said result that we are going to return, just like that. And in the middle here is where we're going to do all of our work. And then, of course, we'll call the function to make sure we're actually doing it correctly. So let's see. Now, the first thing that we want to do is probably something like a while loop, and we need some type of condition where we know keep traversing in this order from go right, down, left, and up until we're done. And that condition is pretty simple. You can either use some type of way to figure out what index you're at to make sure you're within the bounds, or something that's even simpler is we know that the number of elements in our results will be the total number of elements in this matrix. So using that intuition, we can actually write out a cleaner statement. So first, let's get the total number of elements in our matrix, and that's going to basically be the number of rows or elements in a row multiplied, which is the columns, multiplied by the number of rows themselves. So we're saying from the first row, give me the count and give me the number of rows that there actually are. And we can say here now, while result is less than the total number of elements, and this should be results.count, we want to go ahead and traverse. Now, I'm just going to comment out what we kind of spoke through already, and the general pattern I see here is we want to go right, then we want to go down, then we want to go left, and of course, finally, we want to go up. Now, every time we do this traversal, we need to kind of go inner with each of our traverses. So what I mean by that is when we get to 1, 2, 3, 6, and then we get to 6, 9, 8, 7. Once we get to the 4, we don't want to go back to the 1. Otherwise, we're going to end up in this infinite loop. We want to move whatever pointer we have inwards and then start traversing here. And at this point, we'll have 9 elements in our result array, which matches our matrix, so we'll be done. And then we'll return result down here. So the way we can actually do this is pretty simple, contrary to what it looks like. So we're going to keep 4 indices here. We're going to say our left starts at 0, the leftmost of our matrix. We're going to have a top, which starts at 0 as well. We're going to have a right, which starts at our matrix first row dot count minus 1, which will be the rightmost index within our bounds. And then we're also going to have a bottom. And our bottom will basically be the number of rows we have minus 1, which is our last row. Now, as we go in this while loop, we're just gonna basically be traversing in order as these comments, and once we're done with each loop iteration, we're gonna move the pointers. So we're gonna move the left inwards by 1, we're gonna move the top down by 1, we're gonna move the right to the left by 1, and we're gonna move the bottom up by 1. Now, for the actual loops, we can probably just get away with 4 loops here. And the reason for that is we can say, let's see, for, I'm gonna say column in, since when we move the left pointer to the right, we're essentially moving the columns, like the thing we're pointing at, over by 1. We're gonna go ahead and say for column in, left, up until right. So let's see, we have our left pointer here, and we essentially want to move to right. So we're going to use the stride functionality, and we're going to say stride from. We're going to go from the left, and we want to actually go through, which is inclusive of the right pointer, so we don't exclude it, by 1. Every time we do this, we can basically just append to our result array. So we're going to say from our matrix, append. Now keep in mind the first element here in our 2D array is our row, and then it's our column. Now we don't want to set this as 0 because that's not really correct, because we're always going to be appending the topmost row. We want to set this to top, right? So whatever row our top is pointing to, and what we're moving is the column. So that's going to be moving in our stride here. If you're not familiar with stride, it's basically like a for loop. So we're going to be doing this, which will go from left to right. Let me say left to right to make it more explicit. Now we want to go top down. So let's see if I can get away with copy and pasting this and tweaking it. So here, what we're going to essentially be moving is the row. So here I'm going to say for row in stride from top plus 1. And the reason we do plus 1 is you can imagine if we go from left to right, we end up at the 3. We don't want to include the 3 again arbitrarily. So we're going to say from top plus 1 through the bottom by 1, go ahead and append. Now, in this case, we're handling the row. So we're going to say row, and we're in the rightmost column. So we're going to say right for the actual column position. Now let's copy and paste it once more time. Since we want to go left now, we're going to say right to left to be more specific. We're going to be moving the column, and in this case, we're going to say from right minus 1. And again, same intuition. We're at the 9. We don't want to include it again. We're going to say minus 1 starting at the 8. And we're going to say through left, since we're going to move all the way to the left, by subtracting 1, so by negative 1. Go ahead and append to our results let's see, so we're moving the row, which is, rather we're moving the column, which is going to be this guy, and we're at the bottom most, so we can put bottom there. We can go ahead and append that, and our final thing to do here is our final loop, which we're going to want to go up. When we're going up, we're essentially moving the row, so we're going to say for row, in stride from bottom, again, minus 1, so we don't double count something, through, and let's see, we're going to say through top plus 1, and again, we're doing plus 1 for the same intuition. Since we're going to start at the 7 minus 1, so 4, we don't want to go to the 1, we just want to go 1 down from it, so we're going to say top plus 1, and let's see, by negative 1, that makes sense. We now get the row that we're changing in this loop, and we're going to change this to be row, and this to be left, I believe. So this will move the row upwards, and the column we're going to stay at is the leftmost that our pointer is at. And this should be sufficient to actually get the matrix traversed as a spiral. So let's just go ahead and run our code, and then we're going to walk through it once more, make sure we don't have any bugs, and then we'll go and look at the space-time complexity. So we're going to go ahead and say our matrix is going to be a 2D array, and I'm simply going to use the example that's given on the left-hand side. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this case, we can see we should get 1, 2, 3, 6, 9, 8, 7, 4, 5. So that's what it's going to look like. We're going to say our result here will be spiral traverse. We're going to pass in said matrix. And finally, we should probably print it out so we can also see what we actually get back from our function. So I'm going to go ahead and say result is results. Now my console has been putting a bunch of junk in it lately, so I'm also going to put some line breaks there so we can actually ignore all of that nonsense. And let's see what we get. So we get 1, 2, 3. 698745. So I believe that is correct. 1, 2, 3, 6, 9, 8, 7, 4, 5. Let's make it interesting and add one more row. So we're going to say 9, 10, 11, 12. So now we should get 1, 2, 3, 6, 9, 12, 11, 10, 7, 4, 5, 8. So it's not even anymore. So we're going to make sure our pointers account for that. So we're going to go ahead and give it a run, and let's see what we get. 1, 2, 3, 6, 9, 12, 11, 10, 7, 4, and then we go to the right to get 5, and then down to get 8. And that's it. We've traversed the matrix in a spinning spiral-like pattern. Now let's talk through this one more time, and before I do that, let's take a look at the runtime and spacetime complexity. So the runtime and spacetime complexity are both going to be O of n, and the reason for that is we only store, let's talk about space first, we only store n number of elements, n being the number of m times n, so the total number of elements in our actual matrix. So you can write this as O of mn, where O of mn equals the column and row height, so you only need to do one pass and save that many elements. And similarly, this is exactly the same, where n is number of elements in matrix. So we can say elements in matrix, which is more or less one pass. And that's basically how we determine the runtime and space-time of this function. And if you really think about it, even though the code might look a little verbose, it makes a lot of logical sense. Now, there are two little optimizations we can do here, and I can talk through those very quickly. They're very nitty-gritty, but if you want brownie points in your interview, the first thing you can talk about is handling the edge case of this matrix being empty. So you can say matrix is empty, kind of stupid. We can just return an empty array. Ideally, this is given in the question that the matrix will never be empty. You can, of course, write it as a guard as well. And the other optimization has to do with the actual results array that we're allocating here. So we check that the matrix is not empty. Now we already know the total number of elements that we are going to stick inside of our result array. Now traditionally, when you create an array like this, you can continuously append to the end of it, and the array will continue to grow in size under the hood, and it's not proportional to your appends. It actually doubles in size, a very nitty-gritty computer science concept. So what you can actually do is create this array with a fixed size. So we can say, go ahead and create an array, and there's a couple ways you can go about doing this. We can create it as an optional array of integers. So we can say, make this something like this, and we can say this can be array repeating, and we can repeat the value nil for the total number of elements that we want. Now, one thing to keep in mind is when you try to return this down here, it's going to yell at you because it's saying, hey, well, this is an array of optional ints. So you can go ahead and simply compact map this to get rid of all of those optional values. Now, if you do this in an interview, it's important to call out to your interviewer that you don't get this compact map for free, right? This more or less does another loop over your collection of results here. But the good thing about this is you're not unnecessarily having your program continue to grow in the space that it's taking up. Since once you have appended, let's say 9 elements, so we would say 1, 2, 3, 4, 5, 6, 7, 8, 9, you'll get a fixed size of results, whereas if you didn't fix it and simply used something along the lines of this, the under representation of this actual results might add 3 more slots in here. Actually, it'll add more than that to anticipate that you're going to append more stuff to it. So very, very nitty-gritty, like I mentioned, so you don't necessarily have to go that deep. But this is the overall problem, and that is all I've got for you guys today. Spiral traverse, one of my favorite problems, definitely asked by Facebook amongst other companies as well. Hope you guys enjoyed the video. If you have any questions, as always, don't hesitate to comment them down below. Let me know if there's other questions you'd like me to cover. I've also got some system design stuff, interview related, in the works, since there's a big shortage of that for mobile devs across YouTube and just the general web and the material out there. If you haven't liked the video already, don't forget to smash the like button, really helps. Hit subscribe so we can keep growing until the end of this year and beyond. Thanks again for watching. I'll see you in the next one.